Hello everyone, welcome to this session. In the previous session, we arrived at the simplified block diagram of a digital PLL. Okay, so let me just draw that. So in the digital PLL, we have a TDC which converts the phase error to digital bits. We will look at it how it works, and the output of the TDC goes to a digital loop filter which has the gain of proportional path Kp and the integral path gain Ki, and here you feed it to an accumulator. I will write that with its small signal diagram, you can say, or the block diagram. So you have an accumulator like this, where this is Z inverse which models the delay, and this is the accumulated value. The output of the proportional path and the digital path, they add together to give you the final control word which is going to control your oscillator, and then you have digital to analog converter which converts the digital word to the control voltage. This controls the oscillator. Okay, and then you can have the feedback divider as required for the frequency multiplication. This is your reference frequency and this is your output frequency. Okay, the output of the TDC, I call this as dTDC. The output of the proportional path, this is dP. Output of the integral path is di. When you combine them, you get the digital control word df, and df gets converted to the voltage V control, and that is your output frequency. Okay, so your output of the oscillator is still a voltage waveform as it used to be. We cannot change that. Similarly, the input of the TDC, which is the reference clock, and the TDC clock, they are also voltage waveforms. So here, if you look at it, by the way, I will just put everything here in one single block and call it as it is normally called, a digital loop filter. Okay. So here TDC is time to digital converter, and how it works, let us look at it. So the block TDC has two inputs, the reference and the feedback, and the output is a control word or a digital word which is dTDC. When we say it is a digital word, it is like a X bit word. So if we have these two signals R and V like this, R is the reference signal, which is like a reference coming from crystal of or some other source. You have a reference clock. V is the feedback clock. It can be the same frequency or different frequency also if it is there. And what we are going to do is, we are going to calculate this error between these two rising edges as was done in the case of PFD. So if you remember, in the case of PFD, you had up minus down, and depending on your up minus down, you get this error, whether it is like this, or in another case up minus down can be negative also. That was a case with PFT. Now, we do not have the PFT. What we want to do is we want to use this delta t time and convert the delta t time into its digital equivalent. That is what TDC is doing. So, here you have a reference clock period which is capital T. Okay. So, the clock which acts as a reference in the measurement of time is your reference clock itself. Okay. So, this delta t error is now digitized right in some digital word. So, first thing which I will tell here is that in the case of PFT, if you remember, you measured the phase error t and it was like minus 2 pi to 2 pi, it was a linear transfer function. Okay. So, similarly, here if this in the one case you are seeing the error is this, in the other case I can have the rising edge of the clock may be coming like this, so late. Just an example. So, this is the difference between another. The rising edge is delayed and it is delayed by delta t, which is closer to, you can say, one reference period. Okay. Similarly, you can have delta t where the rising edge on R comes after the rising edge on V, and that also period can range from small delta t to a large value of delta t. So, here the range of the TDC which the range of phase error measurement which are normally used, range of phase error of measured by TDC is typically 2 reference period. Okay. So, you can say plus t ref minus t ref 2 plus t ref, it gives you plus minus 2 pi. That is the maximum which you can have or which you will use in general. Now, this delta t is digitized to the control word DTDC. Okay, this delta t timing. So, in order to digitize this delta t timing, you need reference or some resolution. So, this delta t I need to digitize. So, when you have a voltage, for example, delta V, and you want to convert it into discrete value D, what you need is a reference voltage for, or whatever is your comparator threshold. Okay. The digital, this is like analog to digital conversion. Analog to digital conversion requires threshold voltages for comparators. Okay. Similarly, delta t to TDC DTDC requires your resolution delta t, you can say LSB or delta t threshold, delta t resolution or delta t LSB to convert from or you can say this delta t to TDC requires some kind of delta t resolution, okay, or delta t LSB. which what it means is the following. If the phase error is something like this, with just an example, this is R and let us say this is V, and this separation between R and V has multiple, or you can say multiple slots. Each slot is delta T LSB. If such is the case, then you can count how many slots do we have between these two rising edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9 complete slots and the 10th slot is half. So, depending on how you are giving the compared value, you can say the separation between these two rising edges is or this particular value, this delta T is approximately 9 times delta T LSP. So, this is something which you need. Based on this, you can convert your this 9 to a digital word. So, if I have 9 bit 9 as the delta T LSP, my DTDC I can very well write for above case delta T is actually when I found the separation between these two rising edges, it gave me this is approximately equal to 9 times delta T LSP. So, if there is some information about delta T LSP, then taking that into account, I can say my DTDC is nothing but here let us say I am having a 5 bit word. So, I will write 5 dash B, this is just nomenclature we normally use, and this is 9 here. So, 0 1 0 0 1. So, this is this digital word, the placement values are 2 power 0, 2 power 1, 2 power 2, 2 power 3. So, you have equivalent, decimal equivalent is 9. So, this is how you are going to convert. So, if you look at it, what we need from this TDC block is the information about what is the delta T LSP, and the range which we are going to measure is with the TDC normally max that will be -1 reference period to +1 reference period, like the one which we had here. Okay, -1 reference period is -2 pi, +1 reference period is +2 pi. So, this range, so range of the TDC is 2T, and what you have here is the delta T LSP information which you need. So, if n bit TDC, okay, and n bit TDC with range 2 times T implies that your delta T or the resolution delta T LSP is equal to your 2T range divided by n bit TDC. So, you know n bit TDC how much is the maximum value. So, you can say this is approximately 2 power n values you will have. So, this is your delta T LSP. Okay. And the digital word which you are going to get, the digital word will be having a equivalent binary value. Okay. So, what I am going to get, how I am going to write this performance of the TDC. So, given phase error, okay. Now, you have to, because you are doing it digitally, so you have to specify whether you are going to have positive or negative, okay, the phase error. So, here let us say we take that into account later. The whole 2T range which is from -T to +T is given by n bits. Okay. So, given phase error phi error as 2 pi times delta t by t, this phase error is converted by TDC to, you can say, the digital equivalent of. So, you can always write delta t as t over 2 pi times phase error. Okay. So, the decimal equivalent of this value is delta t divided by delta t LSP, which is t divided by respect to t divided by 2 pi of phase error divided by LSP, which is 2 t divided by 2 power n, which in turn is equal to 2 power n by 4 pi times phase error. Okay. So, here the thing is that I have taken the range 0 to 2 t, you can take the range minus t to 2 t also. The only thing is you have to then take into account the positive and the negative. We can take that into account in digital case also. So, this TDC is, if you have a phase error phi r, this phase error phi r is converted to its digital equivalent as you see here. By the way, this is the this is decimal equivalent. Okay. Whatever value you get here, the phase error is actually that value into delta t LSP, but this is what you are going to get from the TDC. This is decimal equivalent, and this you do decimal to binary. You do decimal to binary, so that you get dTDC. Okay. So, if I write dTDC as, though it is a binary value, you can say this is like n bit whatever number you have. This binary value is 2 power n divided by 4 pi times phi error. So, if your phase error is 4 pi is your 2 t, okay, 2 times the time period, your decimal equivalent is 2 power n, your phase error is 0, decimal equivalent is 0, or binary equivalent is 0. So, this is effectively the gain of n bit TDC in general. Okay. So, when you use the TDC here in this PLL, you have a phase error, okay, and this is a n bit TDC, and the n bit spans the range minus t to plus t. In that case, whatever the dTDC value you are getting, I told that I have been using this dash line here. This dash line just means that there are multiple signals. So, if I want to write this as an n bit TDC, I will say it n here. So, this n bit TDC gives you this dTDC. So, if you just look at independently the value of n bit TDC, and n bit TDC equal to some value in terms of 1000 or other things. So, if n is example, right, if n is 10 bit for example, n is 10, in that case, and my dTDC value happens to be something as, let us say it is 496. Okay. This is the numerical value, the decimal value. In binary case, you can say this 10 bit TDC, the decimal value is equal to, this is going to be 0, then you have 256. So, 10 bits will be there, you will have 256, you are going to have 128, then you will have 64, right, and you will also have 32, and rest all are going to be 0, 16, 8, 0, 4, 8, 4, 2, 1. So, what you see here is that the digital equivalent is going to be this, okay, whereas the decimal equivalent is this. Here 496 does not mean the error is 496 times the reference period? Well, this 496 means phase error is actually phase error is, so phase error is 4 pi divided by 2 power n times d TDC. This is what we have. So, it is 4 pi divided by 2 power 10 times 496. This is the phase error value you will see. So, 4 pi times 496 by 1024. This is the phase error which you see. So, what is the meaning of the DTDC output? That is clear by now, that it measures the timing difference between the reference and the feedback clock. What you need is delta t LSB, somehow you have to get it, okay. And once you get that, you have to create this delta t LSB in a similar way as you generate the comparator threshold. Once you get that DTDC, this is what it will mean. Now, a typical implementation, we will not go that much detail, but a typical implementation of TDC is as follows. TDC, there are multiple ways in which you can implement, okay, TDC. So, one way is that, let us say I have delay line. So, okay, this is the delay line which consists of 2 power n delay cells. Okay. So, this I will name this node as Q1, Q2, Q3 and so on, and it goes up to Q in Q 2 power n. So, all these are delay cells. These outputs okay. These outputs are fed to registers. So, if I write it like this, let me just make it a one single and then copy paste. Okay. So, these are fed as inputs and you have a clock here, okay, and this is your output Q. So, this is your register, by the way. So, you have these registers. Normally, what you will see is just a one single line saying that these are registers. Okay, they are not connecting, by the way. I will just disconnect them in a moment. Okay, and similarly, you have on all the cases which you have. So, these are registers which are clocked. So, I am having a clock which connects all of these registers. So, let me just connect this. So, a clock is there which connects all of these blocks, finally, it comes here. Okay. So, this I am going to call as let me call this as R1, R2, R3, R2 power n. Okay. And this clock, what you are seeing here is another signal which is your reference signal, and this is your feedback signal. Now, if I make sure that the delay from here to here, okay, delay of combined delay of 2 power n delay cells is 2 reference period. This is made sure independently. Okay. Then delay of each TD delay of each cell is nothing but 2t divided by 2 power n, which acts like delta t LSB in our case. Okay. So, now just think about it. Let us say when you are having the reference clock coming like this. This is your reference clock, and your feedback clock is coming somewhere here. This is a feedback clock. So, you start looking, you feed these two signals to the to your circuit above with respect to time. Okay. So, when, and let us say all the signals start at time instant t equal to 0. Before that all the signals were actually 0. So, in that particular case, if I look at R1, R2, R3 and so on, I am looking all these values. So, I will look at R1, R2, R3 and so on, you can say R into 2 power n. So, as you see from here, when I just, so these are the registers which sample the value at the rising edge. So, when the first rising edge on R comes, what you sample is 0, 0, 0 and 0, all of them are 0. Then after some time, you see a rising edge on V coming after a certain delay. Okay. If it is after a certain delay that you get rising edge on V, then that rising edge on V is going to propagate through these delay cells after the delay. So, if I look at here, my Q1, okay, Q1 will actually become 1, this is not R1 signal, but I am just plotting, this is your Q1 after the delay, right. Q2 signal will actually become 1 after another delta t LSP delay. Similarly, Q3 signal will become 1 after, so this is Q2, this is Q3, it will become after some delay, right. Since the range of this TDC, this delay line is 2t, right. So, the delay of, you will not, till the time you get the rising edge here, you will not be able to get Q in 2 power n as 1. Okay. So, then what happens is that few of them will still be 0 and others will become 1. So, when you get the next rising edge, at next rising edge R1 will be sampled as 1, R2 will be sampled as 1, R3 will be sampled as 1 and similarly R4 and other values will be sampled as 1 and the some other values will be sampled as 0. Okay. So, you can think about it that the number of flip flops which will register value 1 at the next rising edge. Okay. So, number of flip flops which will register value n at the next rising edge, those number of flip flops you can say, if this whole delay, it will be easy for you to understand like this, if this whole delay is 2 times t, depending on how you choose, you can also choose a range of t. Okay, this is just one example. If you choose a range of 2t, then you can say that 2t minus whatever this phase error is, right. Just an example, this, if this, the delay of the elements till here is delta t, then only the registers which are coming before this, they will register 1, other values will register as 0. So, when you sum up all these register values, right, when you sum up all these register values, you will find that you can easily calculate this one, this delay. So, range is 2t, you have this delta t. So, whatever value you are going to get at that point, right, you can actually find what is the decimal equivalent. Okay. So, what we need is that whatever these register values you get, these register values are saved and these register values are summed up to give you a representation for this delta t error. Okay. So, what you see here is that we need such delay cells. Okay. We need the registers to get the to latch these values, right. There is other way to detect the. So, this is one simple method, right. The important part here is that you need to get this delta t, somehow this has to be tuned, your LSP size is what you require and this has to extend over the whole reference clock period, right. So, this is a simple implementation. There are multiple ways in which you can implement the TDCs. Okay. You can always refer to the literature for that. So, if I just want to conclude the TDC part, the thing is that you require delay cells with delay tuned to delta t LSP. This is important because if the delay of these elements which you are seeing here is not delta t LSP is something else or you do not know, then you cannot comment on what the phase error you have. So, somehow you have to make sure that the delay is fixed or within the margin of error what you can tolerate. Okay. And the number of delay cells, which you require is proportional to your reference clock period. Sometimes you make sure that the phase error is by some other means, by dual loop or something, you make sure that the phase error will not increase beyond this range. You can then limit the range of the TDC, but in general number of delay cells is proportional to the reference clock period. It is directly proportional and inversely proportional to the resolution of TDC, which is also called as delta t LSP. Okay. So, better the resolution, more delta more the number of delay cells. Now, you may ask that whenever you are designing any such things, more number of delay cells will take more area. Okay. So, why we would like to have that? Well, the answer lies that when you are quantizing the phase error. So, you had this phase error if you go back. Okay. So, here if you look at it, the region where your rising edge lies is this. Okay. So, based on your logic, you can say either my phase error digital equivalent is this or count till here like 9 times T LSB, or you can say I will count because it is coming after this, but the other edge I have not got. So, I will count this. So, your digital equivalent, or you can say measured phase error has quantization error limited by, that's a better word, it is limited by mod of delta t LSP by 2. So, actual if you were doing it in an analog manner, then whatever this phase error it is exactly this delta t. Okay. But what you are saying is my phase error is either the value is 9 times delta t LSP, which is actually less than the delta t error, and if you say it is equal to 10 times delta t LSP, which is more than the phase error. So, your actual phase error, whatever you are writing 9 times t LSP, if this is the value of dTdc, okay, if dTdc says the actual phase error delta t gets added with the quantization noise q TDC, okay, to give you 9 times delta t LSP. So, TDC comes with inherent quantization noise, and this quantization noise is limited, QTDC is limited between plus minus delta t LSP by 2. So, you are not measuring the phase error exactly, but what you are measuring is phase error with an in addition to the phase error, in addition to the phase error what you get is a quantization error. Okay. So, the TDC block which is measuring the phase error between R and V signals and gives you dTdC, the small signal model of this small signal model of this can be represented by, you can write I am having a phase error as phi reference and phi feedback. I subtract this phase error and I multiply by the gain. What is the gain of the TDC? Or let me just write as k TDC plus I add the quantization noise q TDC and then I get dTdC. Okay. That is the small signal model of TDC. Okay. If you are not doing any noise analysis, then we can ignore q TDC, but this is what exactly happens, right. And k TDC we have seen it depends on what range you are implementing with how many bits. So, if we are implementing a range of 4 pi, then in that case this is 2 power n divided by 4 pi, this is the k. Okay. So, this is how we will detect the phase error to give us the digital word which is used in the blue filter, which is used by the blue filter. Okay. Thank you.